I just want to do another example. I want to show you that it's not always as simple as just saying that it's the first term that appears in all the partial sums. So let's evaluate the sum from n equals 2 to infinity of 1 over 2n plus 1 minus 1 over 2n plus 5. As usual, we're going to start by writing out some partial sums. So observe first of all that this series starts with n equals 2, not n equals 1. To keep the convention, we're going to say that the partial sum, since the nth partial sum is the sum up to term number n, we're going to say that this series only starts with s2. It doesn't even have an s1 because there is no n equals 1 term. So s2 is just going to be the terms up to 2, which is going to be only the n equals 2 term. So that's going to be 1 over 2 times 2 is 4 and 1 is 5, and then minus 2 times 2 is 5, and 5 is, is 4 and 5 is 9. So that's going to be 1 over 5 minus 1 over 9. S3 is going to be the first term, so we know that this is equal to S2 plus A3, which is 1 over 5 minus, in other words, it's the previous partial sum plus the next term. So 1 over 5 minus 1 over 9 plus, if I let n equal 3, then I get 2 times 3 is 6 and 1 is 7. And then so again, 6 and 5 is 11. So we have 1 over 5 minus 1 over 9 plus 1 over 7 minus 1 over 11. Um, you don't see any overlap here yet, so we're going to have to keep going to see what the pattern is. So if S4 is equal to, write out the same thing, the sum of the first two terms, and then I'll add the third. Or sorry, I'm going to do the n equals 2 and n equals 3 terms, and then add in the fourth. So that's 1 over 5 minus 1 over 9 plus 1 over 7 minus 1 over 11, and then plus 1 over 9 minus 1 over 13. Okay, now we're starting to at least see a little overlap. We have negative 1/9 and positive 1/9. It's kind of strange because if you look how far apart they are, it doesn't really look like we're seeing much of a pattern. So we have to keep going. With some of these you have to keep going to see the pattern. So this is going to be 1 over 5 minus 1 over 9 plus 1 over 7 minus 1 over 11 plus 1 over 9 minus 1 over 13 plus 1 over 11 minus 1 over 15. Now maybe we'll see a little more pattern. We can again cross out the 1/9 terms, and we also have negative 1/11th, and positive 1/11th, so we can cross those out, leaving us with 1/5, 1/7, negative 1/13, and 1/15. Notice that the 1/5 and 1/7 were also appeared in the S4 term, and just to be complete, they also actually appeared here. So those are some good candidates for the terms that are going to remain when we finally write out the nth partial sum. So let's write out S6, 1/5 minus 1/9 plus 1/7 minus 1/11 plus 1/9 minus 1/13, that's a ninth, plus 1/11 minus 1/15 plus 1/13 minus 1/17. Okay, so we cross out the 1/9 terms, the 1/11th terms, and we also see that we now have negative and positive 1/13. So we can cross those out. And what do we have? There's our old friends, the 1/5 and the 1/7th term, and now we have 1/15 and 1/17. So hopefully you can see what's going on here. Is if I write out the Sn term, what we can see is that we're always going to have 1/5 and 1/7. The question is, what do we have to subtract here? So in S4, we had to subtract negative 1/11th and negative 1/13. In S5, we have to subtract negative 1/13 and 1/15. In S6, it was negative 1/15 and 1/17. What we know is that these terms are being generated by we're taking n and multiplying it by 2, and then we're going to add something to it. So, looks to me, if we look at this last one, 1/15 is going to be, that is, 15 is 2 times 6, that's 12, plus 3. So I'm going to say 2n plus 3, and the 17th is 1 over 2n plus 5. How do I know that works? How do I know those are the correct expressions? Let's try it out with some of the other ones. In S4, the terms that remained were negative 1/11th and negative 1/13. Let's take 4, we double it, 2 times 4 is 8, plus 3 gives me 11. 2 plus 4 is 8, plus 5 is 13. So this formula does in fact work for S4, and you can verify that it also works for S5. So this is actually the correct expression for Sn. Now all we have to do is calculate. We know that the sum S is equal to the limit as n approaches infinity of Sn. That's going to be 1/5 plus 1/7 minus, this is going to be infinity, 1 over infinity minus 1 over infinity. And so that equals 1/5 and 1/7 is, that looks like 12. 1/5 plus 1/7, you can work this out, is 12 over 35. So that's the answer. That is the sum of this series. Now, question is, why did I put all this work into figuring out what these terms were? Well, I mean, partly because that's just the definition of the sum of an infinite series. We need to know what the nth partial sum is so that we can find its limit. But some of you might have said, suppose I guessed wrong. What difference would it make? Suppose that I said, oh, I don't know, it just looks like 1 over n plus 5. In other words, these two terms look like I'm subtracting 1 over n plus 5 and 1 over n plus 17. It's like, let's suppose you're really, really sloppy and you don't want to pay attention to what it is, and you just say, come on, the 1/5 and 1/7 are the ones that are going to remain, and the other two are just some term that's going to be infinity. Well, I'll tell you. Sometimes on quizzes and tests, what I like to do is I like to ask people to actually form this term correctly to show that they know how to do it. So you can't always just say, well, it doesn't matter what they are because they're going to be infinity. It is part of the definition, and it is important to understand how to form it.